Today, we are going to learn one of the most important ideas in modern technology. Mathematics is the foundation of artificial intelligence. Many students think artificial intelligence is mainly about programming. Of course, programming is important. We need code to build systems, train models, and run applications. But behind the code, there is something deeper. That deeper foundation is mathematics. Artificial intelligence does not become intelligent by magic. A machine learning model does not understand the world like a human. It processes numbers, detects patterns, calculates probabilities, adjusts parameters, and reduces errors. All of these processes are mathematical. So, when we study AI mathematics, we are not only studying formulas, we are learning the hidden language that allows machines to learn from data. The main message of today's lecture is simple. To understand artificial intelligence deeply, we must understand the mathematics behind learning, prediction, uncertainty, and optimization. When we use tools like ChatGPT, image generators, recommendation systems, or translation tools, they may look very intelligent. They can answer questions, generate text, recognize images, and even make predictions. But we must understand one important scientific fact: AI systems do not think like humans. Humans have experience, emotions, intuition, memory, and consciousness. AI systems do not have human consciousness. Instead, AI systems work through mathematical operations. For example, when a language model predicts the next word in a sentence, it does not feel the meaning like a human. It calculates probability. It looks at patterns from large amounts of text data, then it estimates which word is most likely to come next. So, behind every AI model, there are mathematical functions, probability distributions, vectors, matrices, and optimization methods. That is why this slide says behind every AI model, there is mathematics. This means that if we only use AI tools without understanding the mathematics, we may know how to operate the tool, but we will not fully understand how the system works. Now, let us look at the full mathematical workflow in artificial intelligence. AI usually starts with data, but raw data is not useful by itself. The first step is to understand the structure of data. For example, text, images, sound, sensor signals, health data, sports performance data, and financial data must all be changed into numerical form. AI cannot directly understand an image as an image. It understands the image as numbers. After data is represented numerically, the model tries to extract patterns. This is where learning begins. Mathematical functions help the model find relationships between input data and output results. Then we need probability and statistics. Why? Because real world data is uncertain. Measurements contain noise. Predictions are never perfectly guaranteed. Probability helps AI manage uncertainty, and statistics helps us summarize and interpret data. Finally, AI needs optimization. Optimization means improving the model step by step. The model compares its prediction with the correct answer, calculates the error, and adjusts its internal parameters to reduce that error. So, the complete AI workflow is data structure, pattern extraction, uncertainty measurement, and optimization. This is why mathematics is not a separate subject from AI. Mathematics is the working mechanism of AI. This slide shows different mathematical areas connected to artificial intelligence. The first area is linear algebra. Linear algebra helps us represent data using scalars, vectors, matrices, and tensors. Images, text embeddings, and neural network weights are all represented using linear algebra. The second area is geometry and vector spaces. Geometry helps us understand distance, similarity, and direction in high dimensional spaces. This is very important in search engines, recommendation systems, clustering, and natural language processing. The third area is probability and statistics. Probability helps us reason about uncertainty. Statistics helps us analyze data, calculate averages, measure variation, and test patterns. The fourth area is information theory. Information theory measures uncertainty, surprise, entropy, and information gain. These concepts are used in decision trees, language models, and compression systems. The fifth area is graph theory. Graph theory studies nodes and edges. It is used in social networks, recommendation engines, knowledge graphs, road networks, biological networks, and graph neural networks. The sixth area is calculus and optimization. Calculus explains change. Optimization helps AI models reduce loss and improve performance. Finally, we have numerical methods. These methods help us implement mathematical theory on real computers with limited memory and processing power. So, AI mathematics is not one single subject, it is an integrated system of mathematical tools. Now let us focus on linear algebra. Linear algebra is one of the most important mathematical foundations of AI. It allows us to convert real world information into numerical structures. A single number is called a scalar. For example, height, weight, age, or temperature can be represented as scalar values. A list of numbers is called a vector. For example, if we represent a student using height, weight, age, and exam score, that student can be represented as a vector. A table of numbers is called a matrix. Images are often represented as matrices. A black and white image can be stored as a matrix of pixel intensity values. A color image has multiple channels, usually red, green, and blue. A higher dimensional data structure is called a tensor. Deep learning models use tensors heavily because modern data can have many dimensions. For example, a color image is not only width and height, it also has color channels. A video has width, height, color channels, and time. This becomes a tensor. In neural networks, the basic operation is often written as y equals w times x plus b. Here, x is the input data, w is the weight matrix, b is the bias, and y is the output. This simple formula is used repeatedly inside neural networks. It allows the model to transform input data into useful internal representations. So when students ask, why do we need matrices in AI? The answer is clear because AI models store, transform, and learn from data using vectors, matrices, and tensors. Now we move to geometry and graph theory. In ordinary school mathematics, we often think of geometry as shapes, lines, angles, triangles, and circles. But in AI, geometry becomes much more powerful. It helps us understand data in high dimensional spaces. For example, words can be represented as vectors. The word king may be close to queen in vector space because they are semantically related. The word car may be far away from banana because they are less related. This is called an embedding space. In embedding space, similar items are placed closer together. A common formula used to measure similarity is cosine similarity. It compares the direction of two vectors. If two vectors point in a similar direction, their meaning or pattern may be similar. This is used in semantic search, recommendation systems, plagiarism detection, document matching, and language models. Now, let us look at graph theory. Graph theory studies relationships. A graph has nodes and edges. Nodes can represent people, products, websites, cities, joints in the body, or concepts. Edges represent relationships between them. For example, in an e commerce system, users and products can be represented as a graph. If many users buy similar products, the system can recommend new products based on graph relationships. In social media, people are nodes, and friendships or interactions are edges. In biomechanics, joints can also be modeled as connected nodes, and body segments can be treated as edges. So, graph theory is important because many real world systems are not isolated data points, they are networks of relationships. This slide shows two major mathematical worlds, continuous mathematics and discrete mathematics. Continuous mathematics deals with smooth change. Calculus is the best example. In calculus, we study curves, gradients, rates of change, and continuous functions. This is very important in machine learning because training a model means gradually changing model parameters. The model moves through a continuous loss surface and tries to reduce error. For example, gradient descent uses calculus to update weights step by step. Discrete mathematics, on the other hand, deals with separate values and structured decisions. It includes logic, Boolean values, combinatorics, recursion, trees, and graphs. Decision trees are a good example. A decision tree splits data into branches based on conditions. For example, if income is greater than a certain value, go left. If not, go right. This is a discrete structure. So both continuous and discrete mathematics are necessary in AI. Continuous mathematics helps neural networks learn from smooth changes. Discrete mathematics helps AI systems make structured decisions, process logic, and work with graphs and trees. A strong AI learner must understand both worlds. Now we come to probability and statistics. Real world data is never perfect. It contains uncertainty, missing values, noise, and variation. AI must work under uncertainty. Probability helps us answer questions such as, what is the chance that this email is spam? What is the chance that this patient has a disease? What is the probability that this student will pass? What is the probability that this image contains a dog? One important concept is conditional probability. Conditional probability means the probability of one event given that another event has already occurred. Bayes' theorem is also very important. It allows us to update our belief when new evidence is available. For example, spam filters use probability. If an email contains certain words, links, or patterns, the system calculates the probability that the email is spam. Statistics is slightly different. Statistics helps us understand data from the past. We calculate mean, variance, standard deviation, correlation, and distribution. These statistical tools help us summarize large data sets. For example, before training a machine learning model, we often normalize data. Normalization means transforming data so that variables are on a similar scale. This helps the model learn more efficiently. So, probability helps AI think about future uncertainty, while statistics helps AI learn from historical data. Both are essential. Information theory is another important mathematical foundation of AI. The key idea in information theory is that information is related to uncertainty. If something is very predictable, it gives little new information. If something is surprising, it gives more information. The formula shown in this slide is entropy. H of x equals negative sum of p of x times log p of x. In simple words, entropy measures uncertainty or randomness in a system. If all outcomes are equally likely, uncertainty is high. If one outcome is almost certain, uncertainty is low. This concept is used in machine learning in many ways. In decision trees, information gain helps decide which feature should be used to split the data. In language models, entropy helps evaluate uncertainty in word prediction. In deep learning, loss functions such as cross entropy are used to train classification models. For example, if an AI model predicts the wrong class with high confidence, the loss becomes large. If it predicts the correct class with high confidence, the loss becomes small. So, information theory helps AI measure uncertainty, surprise, and prediction quality. Now we come to calculus, one of the most important subjects for understanding learning in neural networks. Calculus studies change. In AI, we need to know how the loss changes. When model parameters change, a neural network contains many weights. During training, the model makes a prediction. Then it compares the prediction with the correct answer. The difference is called error or loss. Now, the important question is how should the model change its weights to reduce the error? This is where derivatives and gradients are used. A derivative tells us how a function changes when its input changes slightly. A gradient tells us the direction of greatest increase in a multivariable function. In machine learning, we usually want to reduce loss, not increase it. So we move in the opposite direction of the gradient. The weight update rule is new weight equals old weight minus learning rate times gradient. The learning rate controls how large each update step should be. If the learning rate is too small, training becomes very slow. If the learning rate is too large, the model may jump too far and fail to find a good solution. The chain rule is also very important. In neural networks, errors must be passed backward from the output layer to earlier layers. This process is called backpropagation. Backpropagation uses the chain rule to calculate how each weight contributed to the final error. So, calculus is the engine of learning in deep neural networks. Without calculus, modern deep learning would not work. This slide shows the idea of optimizing using a loss surface. Imagine the loss function as a mountain landscape. High areas represent high error, low areas represent low error. The goal of the model is to move from high error toward low error. The best possible point is called the global minimum. This is the point where the loss is lowest. But in real deep learning, the loss surface is very complex. It may contain many hills, valleys, flat regions, and local minimum. A local minimum is a point that looks like the lowest point nearby, but it may not be the best point overall. Optimizing algorithms help the model move through this complex surface. Gradient descent is the basic method. More advanced methods include stochastic gradient descent, ADAM, RMS prop, and other optimizers. These algorithms update millions or even billions of parameters during training. For example, a large language model has a huge number of weights. Training such a model means adjusting those weights again and again until the model becomes better at prediction. So, optimization is the process that turns mathematical models into trained AI systems. Now we move from theory to hardware. In mathematics, we often write ideal formulas, but computers cannot always calculate perfect continuous values. Computers have limited memory, limited precision, and limited processing power. This creates a gap between mathematical theory and real hardware implementation. Numerical methods help us bridge this gap. For example, a smooth continuous curve in theory may be represented by discrete points in a computer. The computer approximates the curve using finite values. This is very important in AI because deep learning models require huge calculations. Matrix multiplication, gradient calculation, tensor operations, and optimization steps must be computed efficiently. Numerical stability is also important. Sometimes very large or very small numbers can cause errors in computation. This can lead to overflow, underflow, or unstable training. Matrix decomposition methods are also important. They help simplify large matrices and speed up computation. In real AI systems, especially those trained on GPUs, numerical methods are essential. So mathematics does not end on paper. It must be translated into efficient computation. That is why numerical methods are important for modern AI engineering. This slide summarizes the full machine learning pipeline. Artificial intelligence is not built from only one branch of mathematics, it is an integration of many branches working together. Linear algebra structures the data and stores weights inside tensors. Statistics prepares the data, measures variation, and helps us understand distributions. Probability models uncertainty and helps predict outcomes. Geometry helps AI understand similarity, distance, and direction in high dimensional spaces. Calculus calculates gradients and supports backpropagation. Optimization updates model weights and reduces loss. Numerical methods allow all of these mathematical operations to run on real computers. So, AI is not an isolated discipline, it is a unified integration of mathematical fields. When students learn mathematics, they are not only solving textbook problems, they are learning the internal logic of modern intelligent systems. This is especially important for students who want to study machine learning, deep learning, computer vision, natural language processing, robotics, data science, and physical AI. Now let us conclude the lecture. Many students feel that mathematics is difficult. That is normal. Mathematics requires patience and practice, but in AI, mathematics gives us power. If we only learn how to use libraries, we can run existing models. But if we understand the mathematics behind the models, we can design better systems, debug problems, improve performance, and create new solutions. For example, if a model is not learning properly, mathematical understanding helps us ask the correct questions. Is the data normalized? Is the loss function appropriate? Is the learning rate too high? Is the gradient disappearing? Is the model overfitting? Is the probability output meaningful? Is the feature space well structured? These are not only programming questions, they are mathematical questions. So, mathematics gives us deeper control over AI. The most important mathematical foundations for beginners: linear algebra, calculus, probability, statistics, optimization, and discrete mathematics. Students do not need to master everything in one day, but they should build step by step. First, understand vectors and matrices. Second, understand functions and derivatives. Third, understand probability and uncertainty. Fourth, understand loss and optimization. Fifth, understand how these ideas work together in real AI systems. The final message is: to understand AI deeply, we must understand the mathematics behind learning, prediction, uncertainty, and optimization. Artificial intelligence is not just code, it is mathematics expressed through code. And when we understand that mathematics, we can move from simply using AI to truly understanding and building AI. That is the real importance of mathematics in artificial intelligence.